this is where we get into the theories of probability, because the question becomes, could there have been such a strand of DNA that comes about by chance? Because the theory, obviously, as you mentioned, of evolution suggests that it's mutations now in the DNA that create all of the change in human life over time. So we'll skip the origin of life problem for just a second, and then we'll. But when it comes to the information string in the DNA, the contention is basically that given enough time, you run the experiment enough times, and eventually you will end up with an evolution that, and combined with natural selection, it preserves the mutations that are good, and you will end up with something that looks designed even though it is not designed. That mutation over time being preserved by natural selection is enough. Why doesn't that work?
There's a mathematical problem, and it's a profound one. My colleague David Berlinski calls it the combinatorial problem, or the problem of combinatorial inflation. Maybe a simple analogy, way to get into it. We know from our experience with software code, writing and using it, that the last thing you want in a section of functional software code is a series of random changes to those zeros and ones. If that happens, you're going to degrade the information that's in that code long before you'll ever generate a new software program or operating system. And Richard Dawkins and many, many others, biologists, have acknowledged that what we have in DNA is akin to machine code, or as Leroy Hood puts it, digital code. It's functioning in exactly the same way. So what we've learned from software writing and using is highly relevant to understanding whether or not the mutation selection mechanism could generate conceivably or realistically new information. And there's a reason that changing software at random invariably degrades the information before you get anything useful and new. And that is because there's so many more ways to go wrong. In any system of digital or typographic or alphabetic communication, there are vastly more ways of arranging the characters in question that will generate gibberish than there are ways of arranging those same characters that will generate something functional. So if you start randomly changing things, you're overwhelmingly more likely to find a gibberish sequence than a functional one. And as we've actually tried to quantify that, how much more likely, the quantitative odds are prohibitive. There's a scientist who worked for 14 years at Cambridge University, named Douglas Axe. Did his PhD at Caltech, went on to do a long-term molecular biology research postdoc at Cambridge to try to quantify this question. How rare or common are the functional sequences that would make a new protein, or a new gene capable of making a new protein? How rare are the functional ones in comparison to the non-functional ones? And for a relatively short protein, about 150 amino acids long, he determined that the ratio of functional to non-functional sequences was about 1 over 10 to the 77th power. Now, to put that in context, there are only 10 to the 65th atoms in the Milky Way galaxy. So what that means is that a random search for a new functional sequence is going to be like looking for one marked atom among 10 trillion, it'd be 1 trillion galaxies of the size of the Milky Way. So, and what turns out that even 4 billion years of life's history is not enough time to solve a search problem of that magnitude. And I go into all the math of this in the book, and it's pretty straightforward. There's only 10 to the 40th organisms in the history of the planet, not enough replication events to search a space 10 to the 77 big. So you're looking at, even in the whole, if you take the whole history of life on the planet into account, you're only going to be able to search a tiny, tiny fraction of the total relevant sequences. So you got a really big haystack, really small number of needles, and very little time to look for them. The bottom line is it's overwhelmingly more probable that such a search will fail than succeed in the known time of life on planet Earth, which means that the mechanism is more likely to, the hypothesis that the mechanism produced new information is more likely to be false than true.